Good morning and evening, everyone. This is the today we're happy to invite Professor Yongyun Hu to give a talk on the influence of internal forcing on atmospheric circulation of irradiated giant planets. And now let's Hu to give the talk. Yeah, Professor Hu, the floor is yours now.
Okay, thanks. Okay, can you see that?
Yes.
Okay. Okay, good morning, everyone. First, I thank Professor Cai Tao for his invitation. I'm very happy to give this talk. This talk is based on our very recent paper. So here, this shows so far we already found more than 5,000 exoplanets. So this gives how many exoplanets we found each year. So this figure shows with different method to find the exoplanet. Here, this group. That's the hot Jupiter. So this group should be Earth-like exoplanets, which has a smaller size, and the size and the mass should be similar to Earth. So, so among the 5,000 exoplanets, it's believed about 10 or 20 are potentially habitable. You can see Earth is here. All the potentially habitable exoplanets have the similar size to Earth. So here, that's our group, have been working on in the past decade. So first, we have been working on planetary climate and habitability. Basically, we wanted to know whether those potentially habitable exoplanets can maintain liquid water, or the surface temperature is good enough to maintain liquid water. The second part is biosignature detection. The third part is atmospheric circulations of giant planets. So today I will briefly introduce the first one. I skip the second part, mainly focus on the third part. So for the first part, we are interested in the tidal located potentially habitable exoplanets around mDOFs, because they have the permanent day side and a permanent night side. So suppose the day side is warm enough to maintain liquid water. Let's say the temperature above 0 degrees C, below 100 degrees C. However, the night side could be too cold. So people worry about atmosphere could collapse on the night side if the temperature, night side temperature is too low. Also, people worry about water can be, completely trapped on the night side if the temperature on the night side is below 0 degrees C. That's for the tidal located potentially habitable exoplanets. People worry about those two questions. So we carried out simulations using climate model. First, we test that with a slab ocean, which means the ocean doesn't move. So on the we can see on the day side, the blue color means open ocean. The temperature above 0 degrees C. This is the CO2 level. So if the ocean doesn't move, we can see the night side temperature much very, very low, below -70 degrees C. So that means the water can be, it's possible the water can be trapped, completely trapped on the night side, even though the day side is warm enough to keep liquid water. Here you can increase in CO2. However, even the CO2 level is very high, the night side is still very cold. So then we carry out another simulation with the dynamic ocean, which means the ocean can move, transport heat from the day side to the night side. So with the ocean heat transport, the night side temperature largely increased. Even for very low level CO2, let's see this one. The night side temperature, day side temperature above 0 degrees C. The night side temperature now is about -30 or -40 degrees C. That means the ocean heat transport really can warm the night side very efficiently. If we increase the CO2 to much higher level, let's see this one, the figure C. The night side temperature already above 20 degrees C, -20 degrees C. So if we continue increasing CO2, for example, this one, we already saw that from this plot. If the ocean doesn't move, there is no ocean heat transport. The night side remains very, very cold. However, if you have dynamic ocean, you consider ocean heat transport, the night side can be very, very warm. Partly because of the greenhouse effect, partly because ocean heat transport a lot of heat from day side to night side, which can warm the night side very efficiently. So basically this one means the globally ice-free. So we really don't have to worry about, even there is the ocean, we really don't have to worry about water would be trapped on the night side. So we also consider if there is a supercontinent on the night side, the ocean heat transport doesn't work anymore. In that case, can water be frozen on the continent? So this is the continent. This blue color means ocean. So we use those parameters. This is the gravity. This is the geothermal. The geothermal would warm the ice sheet from the bottom. With the gravity, the ice sheet would flow. So the maximum ice sheet depth, that's this, we can look at this one. So the maximum ice sheet depth is only 2 kilometers. So we know on Earth, the ocean depth is about 4 kilometers. If this means that only half of the ocean water can frozen on the night side supercontinent, we still have like a 2 kilometer deep ocean on the day side. So here, this is another one, another issue. This is icy world, icy planet, could be a planet or satellite. For the traditional view, when star gets brightening, eventually the icy planet or satellite would become a water world. That's a traditional view, because all the stars should be getting brighter and brighter. So this is the traditional view. However, we carried out a lot of simulations. We show that if the starlight is strong enough to melt icy planet or satellite, actually the climate state should directly jump to runaway greenhouse. You would not have liquid water that can quickly, the temperature increase to above 100 degrees C. The reason, there are several reasons. One is the surface albedo. From ice to water, surface albedo change a lot, decrease a lot. Also, once the ice, it melt, a lot of water vapor get into atmosphere. You would have very strong greenhouse effect. So that causes the climate state. You would not have liquid water. Instead, you would have very, very hot, surface temperature. You would have moist runaway greenhouse state. So that's basically that's for the first part. For the second part, that's what I wanted to talk today. This is a very recent paper published on APJ. You can see Adam Schumann's name still here because this work was initiated by Adam and Yuchun Lian. They worked together. However, unfortunately, Adam passed away. So I took over the responsibility to supervise Yuchun Lian. So eventually get the paper published. We still want to memorize the late Adam Schumann. Basically, for hard Jupiters, this is a very early paper. That should be the first paper by Adam Schumann. He showed that for hard Jupiter, you would have equatorial jet, westerly jet. We call that superrotation. This is confirmed by observation 2. So the left figure you can see the dark area means the night side, the bright area means the day side. You can clearly see the equatorial jet, westerly equatorial jet, superrotation. You can also see, because of the superrotation, the westerly jet stream, the hot spot shift downward, downstream. That's Adam Schumann's early work. So in this figure, he interprets why there is a westerly jet stream over the equator. Basically, that means once you have very strong day-night temperature contrast, you would have stationary Rossby waves. So those waves can generate equatorward momentum transport or convergence at the equator. So that generates the westerly equatorial jet and the superrotation. But for all the studies, they haven't considered internal heat flux. It's believed young hot Jupiters would have strong internal heat flux. Also, observational shows the hot Jupiters are much larger than what we expect. That also means the hot Jupiters would have strong internal heat flux. However, for most previous simulation works, they haven't considered internal heat flux. they just consider the external forcing, the day-night temperature contrast. This is what we wanted to do to consider the internal heat flux. That means you have external forcing, the day-night temperature contrast. At the same time, you have internal heat flux. So how the atmospheric circulations of hot Jupiters or even brown dwarf, how the atmospheric circulation should be like. So we use MIT GCM. Here, this, so the dynamic equation, that's the same as the MIT GCM. So here, that's the key, what we we consider is the thermal equation. So here you can see there is the Q1, Q2. The Q1 is the external forcing, Q2 is the internal forcing. So this is for the how do we cite the external forcing, the day-night temperature contrast? We can look at this one. Actually, we can look at this plot. This is the reference vertical temperature profile. That's for the equilibrium temperature. This is the day side temperature. This is the night side temperature. We also cite a radiative time scale. This means a strong external forcing. This one dashed line means weak external forcing. So the difference between the three, that's just by one order of magnitude. So this is how we cite the internal forcing. The internal forcing actually looks like this one. That's Legend polynomial. You can see this Q2, that's external forcing. We cite the forcing at 200 bars. That means below that level, you no longer have this forcing. Above that level, you would have stochastic, isentropic, random thermal perturbation. I think Adam Schumann has earlier works. He used any dynamic perturbation. Here we use the thermal perturbation. So this is different from his earlier work. So this figure shows, we carried out totally 16 simulations. We can look at on the left side from the top to the bottom. That means increasing internal forcing. From left to right, that's decreasing external forcing. So we can look at this left column. So the internal forcing here is 0. The strongest external forcing. Then when going down, here that's a strong internal forcing, strong external forcing. Then from the left to the right, you have the external forcing becomes weaker and weaker. So first of all, let's look at the left column. We can see from top to bottom, the day-night temperature contrast doesn't change a lot. The temperature gradient still remains the same. However, because the internal forcing becomes stronger and stronger, you would see a lot of fine structures. That shows how significant of the internal forcing. If you look at this one from the left to the right, the day-night temperature contrast become much weaker. However, the pole equator temperature contrast becomes stronger. If you look at this one, this is figure C4. Basically, that means the zonal temperature almost uniform. The equator pole temperature gradient becomes more significant. So that's the temperature distribution global. Then here, this is the zonal-mean, zonal-mean. We can look at this one. We can clearly see the strong westerly jet, the superrotation. From top to bottom, when the internal forcing becomes stronger, this jet stream becomes weaker. And also you can see the jet core slightly going downward. We look at this one, from the left to the right, you can see the equatorial jet stream still remains, becomes weaker. However, the much stronger jet stream developed at high latitude. So that means when the external forcing becomes weaker and weaker, the equatorial jet stream becomes weaker too, but stronger jet stream develop at high latitude. This is consistent with the temperature field. Here we can see the very strong zonal temperature contrast. Here we can see strong temperature contrast between the pole and the equator. So if we separate that zonal-mean to several regimes, we can look at this one, this red box. This means the strong superrotation regime. This means this is actually same as the previous simulations. You have very strong external forcing. You would have a strong equatorial jet or superrotation. Then this is the weak jet stream regime. Then we look at this green one. So let's look at the blue box. The blue box means the strong jet stream at high latitudes. So this is the transition, the green one, the green box. This is a transition between the strong equatorial jet stream from the strong equatorial jet stream to mid-latitude jet stream. Then there is another one, this purple box. We can see the sandwich-like jet streams over the equator. You can see the easterly, westerly winds. You know, one layer that's westerly, another layer that's easterly. So this is the most interesting case I wanted to show you. Let's skip this one. Anyway, for the strong external forcing and weak internal forcing, the jet stream is almost the same as the previous simulations, just considering external forcing. This is the weak superrotation because for this one, you still have the temperature contrast. However, you have the very strong internal forcing that can cancel out part of the external forcing. That's why you have the much weaker equatorial jet stream. This is the, I would skip this one. So that's for the mid-latitude jet stream. We can see from the temperature field, the zonal temperature gradient is weaker. The meridional temperature gradient becomes more significant. That's why you can see the jet stream according to the thermal wind relation, you would have strong mid-latitude jet stream. Here is the transition. Just skip this one. So the last case is the quasi-periodic equatorial oscillation. We can see here. Let's look at this plot. For this plot, we can see this is the vertical axis. This is the time. So with time, you can see the westward wind just going downward. You have downward propagation of westerly winds. Then you, after a couple years, you would have easterly winds. So this is very like the Earth's QBO. That's quasi-biennial oscillation over the Earth's lower stratosphere. So this shows the observational Earth QBO. Basically, it's about 27 months. So this plot shows, how, that's by Alan Plum. He used those plots to interpret how the QBO forms. This profile shows the zonal wind, the easterly wind, westerly wind. So here shows the upward waves. All the waves, the gravity waves breaking down at the bottom of the jet. We can see here and here. So that causes when the waves breaking up there, that gives up the eddy momentum flux to drawing the easterly or westerly jet downward. That's why you have the downward zonal wind propagation. We also found that in our simulation. Here you can see, let's see here, you have the eddy flux. That means the wave breaking here at the bottom of the jet. Then that gives up the eddy flux, momentum flux, then drawing the jet, easterly jet downward. Then this drives the west. You can see this the westward jet, westerly jet downward. When the circulation change, atmospheric circulation change, you would have different thermal phase curves. This is what we saw. You have the very strong day-night temperature contrast. You have the phase curve looks like this. However, if you have a strong internal forcing, let's see this one. The zonal temperature gradient becomes much weaker. So basically, you no longer can observe the phase curve. So that's for the hot Jupiter. Can this model be applied to the Jupiter in the solar system? This is another paper we are going to submit soon. So here, there were also studies about the Jupiter's QQO. They also cite the dynamic perturbation. So here we wanted to use the thermal perturbation to show the internal heat flux can generate equatorial jet oscillation. This is how to set the model. This is the temperature is higher at equator, slightly lower at polar region. Here we set a reference temperature under radiative time scale. So this is the simulation result for Jupiter. We can see this one. This is the temperature. This is the when at 60 millibars. We can see the jet streams. We can see the temperature here is lower. It's corresponding to the easterly jet. When you have easterly jet, you would have upward motion. This color means the temperature lower. We can see the color scale. So here, that's we carried out different simulations with different wave numbers. For wave number 10, it's more close to the QQO. For wave number 5, the oscillation period is longer. Let's see this one. For this one, wave number 2, forcing, the oscillation period should be something like, let's see, it's about 5 years. Then this one is about 4 years. So when you're increasing the wave number, the oscillation period becomes smaller. We can see the two very stringent cases. First, you have very steady oscillation. Somehow, after like 20 Earth years, the oscillation just breaking down. We still, do not understand, what's going on for those two. Wave number 20 and wave number 25. But when you're increasing the wave number, you also see the oscillation, very steady oscillations. So this shows the period as a function of wave numbers. So this is the comparison between the simulation and observation. The red curve, the red dots are from observations. The red curve from our simulation, that's for the Zonal-mean temperature at 6.4 millibar. This is another level, 13.5 millibar. Roughly, the observation and the simulation consistent. However, like here, they are not consistent. Here, they should be okay. So basically, that's what I wanted to show you today. So here is the conclusion. So when the internal forcing is weak, relatively weak, compared with the external forcing, you still see the very strong equatorial superrotation. However, if the internal forcing is much stronger than external forcing, you would see the quasi-periodic oscillation of equatorial zonal winds. This model, the thermal forcing model, can be applied to simulate the observed Jupiter QQO. Thank you.